The first relationship has to do with the fact that when that happens, when you take hang on. Okay. So when you take a right triangle and you draw an altitude from that right angle to the opposite hypotenuse, it is going to create similar triangles. So the first relationship is if the altitude is drawn to the hypotenuse of a right triangle, then both of the triangles that are formed by that are going to be similar to the original triangle and each other. Okay, the symbol for similar is this tilde, this little mark. Okay, so what this means is when you draw this altitude right here from the right angle to the hypotenuse, both of the triangles that are formed, so here's one triangle formed and here's the second triangle formed, both of those are similar to each other as well as the original triangle. Okay, so let's review really quickly what it means for triangles to be similar. Okay, so if we have this relationship that triangle ABC is similar to triangle XYZ, okay, what that would mean is you have these two triangles. If they are similar to each other, then the corresponding pieces match up. So A, which is written first, matches with X written first. B, which is written second, matches with Y. And C, which is written third, matches with Z. And so those would all be equal angles. So angle A and angle X are congruent. Angle B and angle Y are congruent. And angle C and angle Z are congruent. So this is a relationship that is true for all similar triangles. Corresponding angles are equal or congruent. Okay, the other relationship that happens is that corresponding sides are proportional. Okay, so here we see corresponding angles are congruent. Corresponding sides are proportional. What proportional means is that they have the same ratio. So that means if I took these 2 points A, B, this side, over the corresponding side, so again, since we've aligned these in the same orientation, it's easy to see which pieces correspond. So A, B, and X, Y, that ratio is the same for every corresponding pair. So BC over its corresponding pair YZ, you can either use the diagram to see which pieces correspond if they're aligned correctly or in the same orientation, or you can look at the statement. BC and YZ are the second and third points in the statement. And then the other relationship is that CA and ZX would also have that same ratio. Okay, and again, CA is first and last, ZX first and last. Okay, and so that's the relationship. You have corresponding angles are congruent, corresponding sides are proportional. Okay, so what that means is if we took this triangle that gets cut with the altitude and it creates 2 additional triangles that are similar, I'm going to rewrite each one in the same orientation as the original. So notice the right angle is on top, and then we have this smaller triangle here. So I'm going to color code these. So I'm going to rewrite my yellow one here. I'm going to rewrite my blue one here. Okay, and the idea is that you can identify which pieces have to match up. Okay, so here we have, I'm going to rewrite my large one as well. So the large triangle is A, C is my right angle, and then B. So when I look at this blue triangle, okay, so if we pull that blue one out and we reorient it so it's facing the same direction, our right angle in the blue triangle is point D. And the blue triangle has a shared angle. The shared angle is A, so I'm going to label A. A is this, the angle to the left. And that leaves my final angle, which is C, so that final angle has to go here. So that's how you can identify how the pieces match up. And this is also similar here. If we take our yellow triangle, this small one, the right angle is D, so I'm going to place D up there at the right angle. The yellow triangle with the original shares point B. So here's where point B is located. That means I can label my point here at B, and my remaining point is C. And so this is what you're looking at. So the similarity statement that you could draw from this is that triangle ABC, the original triangle, is similar to, and we just orient the corresponding pieces. A corresponds to A, B corresponds to C, and C corresponds to D. And that's also similar to, in the smaller triangle, A corresponds to C, this point B corresponds to B, and this right angle C corresponds to D. And so you could get your similarity statements by looking at that. Now, you can either use the statement to work through problems, or you can use the visual diagram. I strongly encourage, and this will go when this will apply when we talk more about similar triangles. I would always rewrite any similar triangles so they're oriented in the same direction. That way you can see how pieces correspond and match up. Visually, it's way easier to control when you're setting it up visually. All right, so let's take a look at how that would work here for these problems. Okay. So notice here, we take our altitude from the right angle to the hypotenuse, and that's going to create these similar triangles. So if I orient everything in the same direction that the original triangle EFG is oriented, I'm going to have one triangle that looks like this. Notice my right angle is down here to the left, and then my small triangle here. Okay, so what I'm going to do is I'm going to relabel all of these with them all being oriented in the same direction. So in my first triangle, this middle triangle, so I'll label that here. In this triangle, when I identify, my right angle is H, so I label that H. My shared angle is F. Notice that's this lower right angle. And then my remaining angle is G, which means G has to go here. Okay, I want you just to take a moment to see on your own, how would you label this remaining triangle with points E, G, and H based on what I was just talking about by matching the parts? So again, by rearranging them so they all face the same direction, it's easy to see which pieces align. So in my yellow triangle, my right angle is H. I'm going to start by labeling that. The shared angle is E, which is up here, this upper angle. And then the remaining angle is G, so I'll label that here. So this gives me the way that all three of these triangles are similar to each other visually. And so now when I label the pieces, so here I have GH is X. So I'm going to label GHX in both of these cases. I have GF is 12, so I'm going to take anywhere I see a GF and label it 12. I have EG is 9, so I'm going to take anywhere I see an EG and I label it 9. And then finally, EF is 15. There's no place where EF exists on these other triangles. And so I've labeled everything that I can on these two smaller but similar triangles. All right, once that's all done, what you can then do is you can set up a ratio of any two or any triangle with the original. Okay, we want to solve for X. So we're either going to use this middle triangle and leg GH, or this small triangle, leg GH. Okay, so it doesn't matter, you can choose either one. I'm going to show you both. You don't have to do both, you just have to choose one. So let's say we take this middle one. If I say X, which is GH, that corresponds to what length in the large triangle? 9. And that's equal to, and now what you need to do is you need to find two pieces that match, two pieces that you have lengths for. So in this middle triangle, I have a length of 12. Because I started with X in the top of my fraction, I need to start with the other measure from that same triangle, 12. And 12 corresponds to what length in the original triangle? 15. And so now to solve for X, which is what we're being asked to do in this problem, multiply both sides by 9 to get X alone. And if you simplify, 3 goes into 15 5 times, into 9 3 times. 3 times 12 is 36 over 5, and there's your answer. Now, let's say you didn't choose the middle triangle. Let's say you chose the small triangle. If I chose the small triangle and I started with x, x is now this lower base, this lower leg. So that corresponds in my original triangle to a side of 12. And that's equal to the other length that I have in my small triangle is the hypotenuse 9 over its corresponding measure in the original, which is 15. And notice that I get the same calculation here, right? When I multiply both sides by 12, I have 9 times 12 over 15, 9 times 12 over 15. It's going to reduce the same way, right? 3 goes into 15 5 times, 3 goes into 12 4 times, 9 times 4 is 36 over 5. You get the same value. So you can do either one. You don't have to do them both. All right. So it probably took me longer to explain that and the options than it's going to take you to do the second problem, but I want you to try. Like, try this second problem on your own and see if you can find what x is using that same process. And also remember, you can enter your answer as a calculation. You don't have to reduce the fractions. We could have left the answer to this last problem as 12 times 9 over 15. That's fine as well. All right, so let's say we take this problem here. We have a right triangle with an altitude drawn from the right angle to the hypotenuse. That means that it's going to cut that into two similar triangles that are similar to the original. So what I'm going to do is I'm going to redraw my triangles all facing this same direction so I can visually see how they're similar. And if I start, I'm going to go ahead and start with the smaller one here first. So here's my smaller one. My right angle is H, so I'm going to label my right angle here as H. My shared angle is E, so E stays up here. And then my remaining angle is G, so I'll label G down here. Okay. Now, if that's all I want to do, again, you know that you can use either of these triangles. So what we could do is once we create just one of those, we label what we have. GH is X, EG is 25. And once we set that up, that's all we need to know. We can set up our ratio of our unknown x over the corresponding measure in the original 60 equals our second measure in the small triangle 25 over the corresponding length in the original 65. Multiply both sides by 60. And there's your answer, 25 times 60 over 65. Makes it nice and easy. You can get your answer. You don't even need to solve for that middle one. However, I'm going to, just in case you solve for the middle one, this is what it would look like for the middle triangle. Your right angle is H, so we label that. The shared angle is F, which is this lower right angle. And then the remaining angle is G. Label what you have. GH is X, GF is 60. So there's your measurements. And you could have set the ratio of X over its corresponding side, 25. Is equal to the other known side 60 over its corresponding side here 65. Multiply both sides by 25 and notice you get the exact same calculation. Okay, either way, you get your answer to be, if you've simplified it, 300 over 13, but you can enter it in any of those forms. Okay, the calculation, or the fraction. All right, questions on that concept. So that's the first concept, the idea that you can create these similar triangles when you draw in that altitude. All right, the next relationship that we're going to talk about includes the definition of something called the geometric mean. So we'll need to define this really quickly. The geometric mean is defined as the number, which we'll call x, that you can place in a fraction or in a proportion so that they two fractions are equal. And so it's going to satisfy the relationship that a over x equals x over b. Okay, so it's the value between a and b that allows you, or that gives you the same ratio for both. A is to x the same as x is to b. Okay, so this is one form of the geometric mean. And now we can take this equation and we can manipulate it in two different ways to get two additional equation forms for this. So this is the proportion, geometric mean. If you cross multiplied right here, you would get x times x, which is x squared equals a times b. So this is another relationship that would hold true for the geometric mean. And then finally, if you wanted to, or if you remembered, if you extract your root for both of these, take the square root of both sides, you would get your third form of saying this. Okay, I don't care which one you choose. I will likely begin with this, I'll start with the definition each time. Okay, but do realize if you remember that final part, it's just the calculation and it's easy to enter it into your answer field. Okay, so if you're trying to find the geometric mean of two numbers, and those numbers, because we're dealing with, geometric elements, these numbers refer to side lengths or lengths, so they are going to be positive values. Okay, so if you take 13 and 27, we want to find what number x gives you a ratio 13 is to x as 27, as x is to 27. And what number can we put for x where this is a true statement? And so cross multiply, x squared equals 13 times 27, extract your root. Notice I wound up going through all three of these forms, and I get my answer to be the square root of the product 13 times 27. The decimal equivalent to that, again, you can enter that as your answer. You could have simplified, combined the product here. All three of these would be acceptable forms of this answer, but that is your geometric mean. Okay, so the final slide is going to have some calculations or some definitions, or these final two slides are going to have like sort of formulas based on geometric means, and so it's going to rely on this equation here. All right, so let's take a look at those. These last two relationships are taking that same figure, right, where you draw the altitude from the right angle, or you take a right angle, draw an altitude from its right angle to its hypotenuse. Okay, so this altitude that's drawn, this altitude CD, that's drawn from a right angle to a hypotenuse is the geometric mean of the segments of the hypotenuse cut off. Okay, so what that means is it's the geometric mean of these two values. And so once again, there's a number of different ways that you can write that. The first is that if you take AD is to CD as CD is to DB, okay, and if you cross multiply, you get CD squared is equal to AD times DB, which means when you extract your root, CD is equal to the square root of AD times DB. Okay, so any of these forms here, before the radical, are sort of the acceptable forms. The one that's normally kind of used is this one. Okay, and so the equation form for this generally kind of states that this altitude to the hypotenuse squared is equal to the product of the two segments cut off, so AD times DB. So that's sort of the form that is generally used in that. However, it leads directly to this form. So again, I don't care which pattern you start with, okay, but see if you can calculate the answer to these two questions here. Try each of them using that formula. The distinction between this and the very first problem that we talked about, you don't have all three side lengths of your original triangle. Okay? And so here you're using one of these geometric mean theorems. Okay? So if we start, here's our altitude from the right angle to the hypotenuse. So that squared is equal to the product of the segments on that or the segments of the hypotenuse that are cut off. So 6 times 10. And if we extract our root, we get our answer to be the square root of 60. Again, nice and easy, nice and quick calculation. The calculated value or the calculation can be used to enter your answer. Okay, the second problem here, same idea but slightly different piece of the problem that's unknown, but it's the same relationship. When you draw your altitude from the right angle to the hypotenuse, that squared is going to equal the product of the two segments of the hypotenuse that are cut off, so x times 11, which means if we divide both sides by 11, we get our answer. So 9 squared, which is 81 over 11. Once again, it's a quick calculation for that. And you can enter it as the decimal value or leave it as the calculation or the fraction. All right, so that's the first of these geometric mean theorems. There's a second one to think about, and that's if your unknown is the leg itself and not the altitude or the segments cut off by that altitude. So the final example, or the final property, is that if you have an altitude from the right angle or to the hypotenuse in a triangle, it's going to cut the following relationship. Okay, so here what this is saying is when you draw in this altitude right here and cut off the hypotenuse, there's going to be either of the legs, so whichever leg that you're finding. So let's say we take this BC. BC squared is going to equal the product of the adjacent portion of that hypotenuse, which is BD, times the entire or the whole hypotenuse, AB. Okay, and if we were finding the relationship of this other leg, then this other leg is the geometric mean, meaning it fits that pattern x squared equals a times b. So AC squared is equal to the adjacent segment of the hypotenuse, AD, times the entire hypotenuse, AB. And so those would be your two possible equation forms for this. All right, so once again, see if you can use that geometric mean theorem where you're finding the unknown leg, okay, from those formulas. All right, so once again, what we're looking at here is when we have this altitude from the right angle to the hypotenuse, what we can see is that this leg squared is the geometric mean of the adjacent portion of the hypotenuse, which is 3, times this whole hypotenuse, which is 3 plus 9. So when I extract the root, I get the square root of 3 times 12, which is 36, and square root of 36 is an integer value, so we can answer 6. Okay, and this last problem here, same process. The altitude from the right angle to the hypotenuse is going to cut this off where your leg is the geometric mean. So x squared is equal to the adjacent segment of the hypotenuse times the whole thing. And so when we extract the root, we get 9 times 13. Again, you can leave your answer as a calculation here. You can work through and simplify. Okay, but any of those forms would be acceptable. I would probably leave it in this form right here. The decimal equivalent, 1082, is also acceptable. But any of these forms, so you can simplify your radical, but you can, since you can enter a calculation, I would do that, and we'll save you that little bit of time.